The power system restoration problem is practically as old as the electric system itself. Modern societies have become increasingly dependent on reliable electricity, therefore major disturbances in the power system have significant impact on both society and economy. Thus, disturbances should be resolved as quickly as possible. If a blackout occurs, the utilities responsible for the operation of the power system should restore the system back to normal operation as soon as possible using power system restoration processes. Fast and robust processes are important for successful system restoration and to limit the adverse impacts of blackouts. Blackout occurrence is unpredictable and blackouts affecting large geographical regions or even entire power system are rare. Today, many power systems are planned and operated using an N-1 principle, which means that the power system should withstand any single fault, including the most severe faults, determined by the system planning criteria. Although system-level blackouts are rare, the risk of a blackout occurrence cannot be ignored in system operation. For example, extraordinary events outside the power system planning and operation criteria may lead the system to operate beyond its operational security limits. Such high-impact, low-probability HILP events are typically unpredictable chains of events with very low probability. However, if such a chain of events occurs, it will have high impact on the security of electric supply. Restoration strategies. There are three main power system restoration strategies. 1. Top-down restoration. 2. Bottom-up restoration. 3. Hybrid, above-both combination. In addition, these strategies may be used simultaneously as a hybrid strategy. Also, intentional islanding may be used to form an automatically disconnected islands with sufficient generation and load. The islands could then be used as starting points for the selected restoration strategy. Top-down strategy. In top-down strategy, the restoration starts from a strong voltage source such as a neighboring power system or a strong island system which, for example, has been intentionally disconnected from the power system just before the blackout. First, the sufficient high-voltage transmission network is restored. After that, the restoration continues to the lower voltage transmission networks and distribution grids. Advantages of top-down strategy. The advantage of the top-down strategy is that the strong voltage source makes it possible to directly restore a high-voltage transmission network that typically covers large geographical areas including both generation and consumption. This reduces the need for complex and time-consuming restoration procedures required in weak systems and consequently expedites the restoration execution. Disadvantages of top-down strategy. The disadvantage of the top-down strategy is that it requires a strong voltage source. If such is not available, the strategy is not possible. Let's discuss bottom-up strategy. Bottom-up strategy, the initial energy is provided by, for example, a black start generator which performs the initial transmission network restoration. At this stage, the system is weak, i.e. the short-circuit current level is very low. After that, the island is expanded by connecting local load and generation. When sufficient generation is connected to the island, i.e. the short-circuit current level is sufficient, the restoration may proceed towards the high-voltage transmission networks. Advantages of bottom-up. The advantage of the bottom-up strategy is that it enables power system restoration also when the top-down restoration is not possible. Disadvantages of bottom-up. The disadvantage is, however, that a black start generator or other similar voltage source within the power system is required. In addition, the management of the extremely weak network may make the bottom-up restoration more complex and slower to execute than top-down strategy. The restoration process typically includes at least the following tasks. 1. The determination of the system status after a blackout. 2. The preparation of black start and other generators for the startup. 3. The preparation of the transmission network and other relevant power grids for the energization. 4. The restoration of the selected transmission networks and power grids. 5. The formation of island power systems by connecting generation and consumption. 6. The reconnection of islands to each other. These tasks can be executed sequentially or in parallel from different locations in the power system as per need. Verification of the restoration actions requires a variety of simulation tools. For a power flow analysis study, for example, the reactive power balance, steady-state voltages and thermal loading of the transmission lines. 5. In addition, time domain dynamic analyses are required to study, for example, frequency variations during load restoration and rotor angle oscillations. 6. Both EMT simulations are required to study switching transients and harmonic interaction during restoration, and short-circuit current calculations are needed to evaluate the relay protection performance. 7. Furthermore, long-term dynamic simulations may be needed to study load restoration and the cold load pickup effect. 8. The resources required during restoration should be allocated, and the detailed instructions should be prepared, documented, and trained. 9. Special attention should be given to the documentation format of the restoration plan so that it is easy to follow in case of an emergency. 10. In addition, the technical reasoning behind the selected restoration strategies and guidelines should be documented. 11. Dispatcher training simulators DTS or operator training simulators OTS have become an important tool for training dispatchers and control center operators. A DTS/OTS makes it possible for operators to perform exercises on various emergency scenarios using the SCADA user interface and displays. 12. In addition, SCADA integrated machine learning and knowledge-based systems may also assist the operator in decision-making during restoration execution. Since simulation models have a major role in restoration planning, it is essential that the models are properly validated to represent the phenomena of interest. For example, the analysis of North American 2003 blackout discovered that simulation models showed stable system operation while undamped oscillations were observed in the real system. 13. Regulation and legislation such as specify mandatory and regular tests on black start generators and its black start function. Therefore, many TSOs perform such tests. However, some TSOs also perform field tests to verify that black start generators can restore the transmission network, which may be used to supply startup power for other generators that do not have the black start functionality. Past major incidents overview. Depending on its operating point and defined constraints, a power system finds itself in one of the predefined states. Figure depicts possible operating states of the power system, including different types of controls and contingency effects that facilitate the transition between these states. These states depend on the operational characteristics of the power system, and each jurisdiction can have its own definition of these states. For example, the European Network of Transmission System Operators for Electricity ENTSOE defined these states as follows. Normal state means a situation in which the system is within operational security limits in the end situation and after the occurrence of any contingency from the contingency list, taking into account the effect of the available remedial actions. Alert state means the system state in which the system is within operational security limits, but a contingency from the contingency list has been detected, and in case of its occurrence the available remedial actions are not sufficient to keep the normal state. Emergency state means the system state in which one or more operational security limits are violated. Blackout state, also in extremis state, means the system state in which the operation of part or all of the transmission system is terminated. Restoration state means the system state in which the objective of all activities in the transmission system is to re-establish the system operation and maintain operational security after the blackout state or the emergency state. The objectives of power system restoration PSR are to enable the power system to return to normal conditions, i.e. normal or alert operating state securely and rapidly, minimize restoration time and associated losses, and diminish adverse impacts on society. You can see international practices by Australia AMO, Brazil, India, Ireland, Italy, France Restoration Test, Italy Switzerland Restoration Test, USA. However, with the development of new technologies, many SOs are utilizing drones to patrol their transmission corridors in order to assess the damage. Using drone technology has significantly decreased the amount of time it takes to assess a SO's system following a disturbance. Other new technologies, such as smart meters, have allowed SOs to determine the outage area in a shorter amount of time. Similar to drone technology, smart meters allow SOs to gain situational awareness of their systems without having to dispatch personnel to customer sites to determine whether they were impacted by the disturbance. In the USA, SOs have identified transmission corridors that are critical to restoration processes. Hardening of these corridor structures against weather impacts greatly reduces the impact to these critical corridors needed to restore the system. Depending on the disturbance, equipment can be damaged and requiring replacement. Many SOs identify staging sites where they stage spare equipment that may be needed to repair transmission corridors. Staging sites should be reviewed to ensure they are not susceptible to flooding or other weather-related events that would make them inaccessible. Lastly, communications are critical during a restoration event. While many SOs have radio systems to communicate with their crews, the ability to communicate across a large geographical area in the event of a communications failure would prove to be very difficult. Continuing to investigate new technologies that can communicate data and voice across large geographical areas would be beneficial as a backup communication source during a restoration event. Operator training for restoration operator errors and remedies. Analysis of the recent emergencies and blackout incidents suggests that mistakes by system operators are a significant contributor, being just the second main cause of these events, with natural disasters being the first. The consequences of system operator errors, i.e. their extent and severity, depend not just on the current power system state and available remedial actions, but also on operator actions and the available and activated defense measures from predefined defense plans. Generally, operational mistakes can be attributed to several reasons, such as insufficient situational awareness, mistakes in control decisions due to incomplete mental model of the process or incomplete analysis, incorrect interpretation of constraints, incorrect interpretation of conditions under which protection acts, misjudgment of the effects from the initiated control actions, misunderstanding in communication. Based on the above listed reasons, available and related defense measures can be identified. These measures are divided in two main categories. Measures aimed to reduce the likelihood of such events. Measures aimed to reduce the impact of such events. Restoration in the future. TSO's experience and knowledge are mainly based on a traditional power system, where conventional generators have an essential role in maintaining the system's security. It is now possible for system dynamics to be monitored in real time by control room operators or analyzed in the operational planning timeframes, depending on the specific power system, e.g. level of renewable energy sources, residential penetration, size, and stability conditions. In the future, the power system is expected to become more dynamic and less stable if no additional measures are taken. It is expected that frequency stability will deteriorate as the system's synchronous inertia decreases, the short-circuit power levels across the network will become more volatile, and there will be more scarce and distributed voltage control resources. Currently, there is very limited provision of ancillary services, such as voltage control or balancing, by RES. Furthermore, it is still not common practice to redispatch, e.g. curtail residential for congestion management. There is also no restoration service capability yet in RES. It is also the case that TSOs currently have little or no observability and controllability of residential, both factors being a prerequisite for coordinated power system restoration. This transition requires SOs to make a paradigm shift to a more diverse and decentralized set of resources to actually control and restore the power system, including vertical TSO, DSO, and horizontal TSO coordination, together with a new set of awareness and decision support tools, which include the measurement and analysis of system dynamics using WAMS and DSA. Moreover, the increasing integration of power electronics into the power system creates new possibilities to effectively use the available technology. Impact of transition to residential on restoration. The increasing penetration of RES, especially based on wind and solar energy, introduces a volatile production pattern in the generation mix due to its intermittent nature. During system restoration, SOs have as common practice to still use conventional power plants to restore the power system, making the process stable and predictable. In a future where less or no synchronous generators are going to be available, it is important to rethink the restoration strategies, using all technologies available in the power system with the capability to provide support. Due to the fact that the share of residential and distribution networks is nowadays significant with the tendency to grow, there is a need for TSO. DSO integrated restoration plans, which will involve increased coordination, information exchange, joint operator training, and most likely common tools. Impact of distributed generation penetration levels on restoration. Although restoration tasks for TSOs and DSOs are generally quite similar, since they are based on predefined operational criteria, their allocation between participating control centers can differ significantly. This tends to be strongly dependent on the penetration level of decentralized generation. Different levels of decentralized generation require different involvement from the DSO, as explained next. Passive DSO. DSO. A DSO without any DG is categorized as a passive DSO. The main task for a passive DSO is to connect load. In this case, from the perspective of the DSO, all restoration strategies will end up in a top-down scenario with the main task being voltage control. Low DG not controllable. The DSOs with low DG penetration may also be treated as passive DSOs from an operational perspective. At the DSO level there is DG, but it may not be observable and/or controllable. In the restoration preparation phase, all DG should be disconnected from the system, insofar as this is possible. This will lead to automatic resynchronization and provision of reactive power by the remaining DG. The TSO must for the first time consider DG and feed in its restoration strategy. After providing reactive power to the DSO and connecting load, DG may automatically synchronize and feed in maximum power. High DG not controllable. In this case the DSO is still passive, operationally speaking, but the DG can be observed. From the DSO point of view this case is critical. The DG is needed for restoration, but cannot be controlled. The reversed power flows may lead to congestion in the DSO grid, both on lines and transformers. The fast-changing load on DSO lines lead to fast-changing voltage profiles. HVDC links. The functionalities of HVDC links can be utilized in order to aid the system restoration, including providing active and reactive support during black start and building of the cranking path. Two types of HVDC links can be distinguished when installed in the power system: HVDC interconnections between synchronous areas SAs and embedded HVDC links within the same synchronous area from pure AC to hybrid AC-DC systems. From an HVDC interconnection it is expected that it will provide support from the healthy SA, whereas from the meshed HVDC link it is expected that it will mainly provide power flow control. Both types of links, depending on the technology, may provide voltage control. Whereas HVDC links are not commonly used for providing restoration service, their participation is expected to increase in the future. The use of the HVDC in the restoration process depends on the technical characteristics related to the type of technology as described below. Line Commutate Converter LCC HVDC. The LCC HVDC is a mature, thyristor-based technology with the highest power rating and efficiency. LCC can provide very fast active power regulation, primary frequency regulation. For this, it needs a high level of short-circuit power. It is furthermore characterized by a technical minimum of transmitted active power. Finally, there is a relatively high risk of commutation failure. Relating to restoration strategies, the LCC HVDC can be used as a target group load with a big regulation capacity. In conclusion, LCC can be used in the bottom-up strategy. For the operation of LCC HVDC, a certain short-circuit power level is required. Energy storage systems. Battery energy storage systems BESS can be used in several ways for supporting the restoration process. In the participation of storage in the load restoration is discussed. An operating strategy for BESS as both load and generator during restoration is proposed. In it is critical to maintain system frequency stable to avoid any further outage or cascading events. Load pickup is one of the most important tasks to keep generation load balance for a stable system frequency. In current industry practice, small loads are suggested to be picked up incrementally to avoid any unstable frequency dip. However, slow load pickup may prolong the system restoration process. As the fast response energy resources, battery storage system BSS. This strategy is highly dependent on the battery's charging and discharging capabilities. In the optimal size for batteries is determined, aiming at providing frequency support during the restoration process. In South Australia, there currently is a 100 MW 129 MWh BESS installation at Hornsdale, and a 30 MW 8 MWh BESS installation at Dalrymple. One of the aims of these batteries is to provide frequency control ancillary services. Successful operation was demonstrated on December 14, 2017. The battery in Hornsdale discharged with millisecond response to immediately arrest the frequency excursion following a trip of a 560 megawatts coal-fired power plant. On a smaller scale, retailers in South Australia are implementing small-scale virtual power plants. 2 recent government-launched schemes could see 90,000 new batteries with up to 400 megawatts of controllable storage connected to the network at the distribution level. WAMS support for system restoration. Fast system dynamics resulting from the integration of PEID adds complexity to power system operation. Wide area monitoring systems based on phasor measurement units (PMUs) are being used by system operators worldwide in the operational environment, giving the control room information about the dynamic behavior of the network and, consequently, increasing awareness for system dynamics. Next to the improved situational awareness and decision support, the synchrophosor technology in the control room can definitely contribute to power system restoration. When compared to traditional SCADA measurements, synchrophosors have an added value of synchronized voltage phase angle information between areas that have to be re-energized and/or reconnected, which can significantly benefit the restoration process.